Now, in this lesson, we're going to take another look at confidence intervals for the mean, but we're going to fill in the details as to how we can do this when we have small samples, or in particular, when the population standard deviation is unknown. In order to use that normal distribution that we learned about in the confidence intervals for the mean in the prior section, the theory states that the population standard deviation must be known, right? So sigma has to be known in order to use that normal distribution. And that's just generally very impractical. I mean, how could you know your population standard deviation if, number one, you don't even know the population mean because that's what you're trying to estimate? So how could you possibly know the population standard deviation? Because the formula for a standard deviation includes the knowledge of the population mean. So it's just not really practical. And at best, we're generally just using estimates for that value anyway. So in reality, what many statisticians do is they substitute the sample standard deviation for the population standard deviation. And that's generally not really a problem as long as you have a large sample. If you've got a small sample, however, then the problem that occurs here, the effects of this problem become more pronounced, and using small samples can lead to very poor results for your confidence interval. So, for this reason, we have another distribution altogether, just a completely different distribution that's used in place of the normal distribution, which is called the student's t-distribution. Now, the student's t-distribution has kind of a unique history. It was created by a statistician by the name of William Seeley Gossett, and he published his results under the name student. And the reasons for this are speculated, but as the story goes, the Guinness Brewing Company tried to hire a statistician to put on their team because they, very forward-thinking here, felt that having, a statistician could help them create a better product, which was incredibly forward-thinking for the 1800s. I mean, it wasn't really until the 1980s that the United States automobile industry started accepting the conceptual use of statistics in order to produce better results. But anyway, they hired a statistician right out of college, and what he started to discover is the problem of using small samples. And the work he was doing often yielded the incorrect results because he was using small samples, whereas the statisticians of the day were using larger samples and didn't have this effect. So he, along with the help of other statisticians, collectively developed the student's t-distribution. And the reason it's called student's distribution instead of Gossett's distribution, again, is speculative, but the prominent concept is that Guinness did not want their statistician publishing mathematics under his own name, because then it would be known to other brewing companies that they had a statistician on board, and felt that if that was known, then the other companies might decide that they also needed a statistician on board and therefore lose their market advantage. It's not entirely certain as to whether that's the truth or not, but it does make sense and it is a good story. But anyway, let's turn our focus here to the practicality and how we actually use the student's t-distribution, because now it's a much more important distribution than it was, because uh, it was discovered that it not only has practical uses for small samples, but also when the population standard deviation is not known, which is basically always. You can't really know a population standard deviation in most cases. Now, the t-distribution, it's not a single curve. So the normal distribution is just one bell-shaped curve. But the t-distribution is actually a family of different bell-shaped curves, and you pick the bell-shaped curve on a parameter known as the degree of freedom. All right, so the degrees of freedom is known as the number of free choices in a sample. And that's always just going to be one less than the size of our sample, for any of our purposes here. So in general, we can just say the degrees of freedom is just one less than the sample size. And you can kind of think of it like this. Like if you have a classroom of students that are going to come in and sit down in a room that has 30 chairs, and you have 30 students that are going to walk in. Well, the very first student that walks in has a choice of where they want to sit. They have a free choice of chair. So they pick one. Now, there's 29 chairs remaining, so the second student that walks in doesn't have as many choices, but they still have free choice. The second to last person only has a choice between two different chairs, but they still have a free choice. The last person that walks in, however, gets a chair, but they don't get to choose what their chair is. Their chair is chosen for them by what everybody else picked. So the number of free choices in a sample is just one less than the sample size. All right, now the degrees of freedom will determine which one of the many different t-distribution curves that you're going to be working with. And it's important, you have to know that value in order to calculate any probabilities or find inverses. It's notable that when the degrees of freedom is greater than or equal to 30, the t-distribution actually looks very much like a normal distribution, but when it's less than that, the peak is not as high and the tails are a bit wider. So for instance, in this diagram right here, this is our normal distribution. And the other curves here in orange, these are t-distribution curves, but with a small number of, let's say this one right here, let's say this has maybe 15 degrees of freedom. And then this one maybe has 5 degrees of freedom. I'm just, hypothetically speaking. But the fewer degrees of freedom that the sample has, the peak of the distribution isn't quite as high. And the tails of the distribution are a bit wider. So you can tell that there's a pretty big difference here between the height of the peak for 5 degrees of freedom and the normal distribution. And then the tails are certainly a bit wider as well. And so when you have fewer than 30 in your sample, these pronouncements can make a difference in your calculations. When it's above 30, it's generally not that problematic. So many textbooks actually kind of use a rule that says if you're using a sample where n is greater than or equal to 30, just go ahead and use the normal distribution. But we use a different rule, and it's actually a bit more common to use this rule. If your population standard deviation is known, then you'll use the normal distribution. All right? If the population standard deviation is unknown, then you'll use the t-distribution. So that's how we'll choose. So it doesn't really matter like what size sample you're working with. You can be using a sample of hundreds of items and you can still use the t-distribution. You can use the t-distribution with any size sample. And in fact, it may have actually been just a time involved in calculating the t-distribution values historically, because the larger your sample size, the more involved the calculation is for your t-distribution values. So possibly after 30, it doesn't make that much of a difference, and so statisticians would just then use normal distributions, which are a much easier calculation than t-distributions, and likely wouldn't have taken as long on current technology. But with newer technology, perhaps that difference doesn't really make a whole lot of change here. Here's an app that demonstrates the t-distribution and actually can calculate some probabilities based off the t-distribution. The t-distribution curve here is in green, and the normal distribution curve is in blue, just so you can see a comparison as to how close these things really are. So for instance, I have set 10 degrees of freedom, and you can tell they're actually fairly close to one another. If I change the number of degrees of freedom and I bring that down, you can see if I go down to 1 degree of freedom, well then there's a very large difference between the t-distribution curve and the normal distribution curve. The way you calculate probabilities is still the same. Okay, so for instance, this is set to left-oriented calculation. So the area under the curve for the t-distribution up to z equals negative 0.36. That area is, I can't remember which one I set as the normal distribution and which one I set as the t-distribution though. Let's see, I bet we can figure it out if we put it to this point. Well, maybe even further down. Okay, so here the t-distribution have to be the larger one. So the t-distribution is the second one. All right, but you can see that, so this is the area for the normal distribution up to the given z-score. And then this is the area under the curve of the t-distribution. So, there's a fairly large difference here. If I increase the number of degrees of freedom, that difference decreases. And once you reach about 30, that difference starts to become fairly negligible, right? And the thing is, you can continue increasing the number of degrees of freedom till whenever. I've only set it here. There's a numeric reason 68 is about the largest you can do here, based off of how I'm calculating t-distribution values in the app. But you can continue going on, and the larger number of degrees of freedom will only mean that that particular curve looks more and more like the normal distribution curve. Now, it is important to kind of mention here, these never are exactly the same. All right, so even with the largest amount of degrees of freedom I can use in this app, there's still a bit of a gap, and there always will be. It's just that gap can become so small that it's not really going to be much use in terms of the precision that you're using in your particular computation. But there always is a difference, so it's generally okay to just use the t-distribution whenever you need it, and that would be when the population standard deviation is unknown, and use the normal distribution if you happen to know that population standard deviation. And that's generally how we go about deciding. All right, so then how does the technology that we have work in terms of t-distributions? Well, surprisingly similar to how normal distributions work. In fact, the TI-83 and 84, it's almost identical. So for instance, um, you have three functions available. You have tPDF, tCDF, and inverse t, all available in your TI calculator. tPDF, just like normal PDF, is not something we're going to use in the class. It will draw a nice looking t-distribution curve if that's what you want, and sometimes maybe you want to look at that bell-shaped curve, but generally you want the area under the curve, and that's what tCDF does. This is what is going to calculate the area under the curve, and therefore it is used for probability. I could spell for probabilities. Okay, now if you'll recall the way that normal distribution function worked, we had normal CDF. It took up to 4 inputs. There was a lower bound of a shaded region, an upper bound of a shaded region, and then a mean and standard deviation optionally could be provided. And what it would do is it would take these lower and upper bounds and calculate z-scores for those. And after it calculates those z-scores, then calculate the amount of area between those values. Okay, tCDF is similar. It takes 3 inputs here. These inputs are going to be the lower bound of the shaded region, the upper bound of the shaded region, and the number of degrees of freedom. But notice there is no place to put a mean and standard deviation. So it will not do the automatic calculation of z-scores for you. We technically call them t-scores with the t-distribution. It looks the same. Like a z-score would be x minus the population mean divided by the standard deviation. But with t-distributions, there's an equivalent formula. It's just all based off of sampled data because we don't know the value of the population mean, so we use x bar instead. And we don't know the value of the population standard deviation, so we use the sample standard deviation instead. And so this we call a t-score. It's the same concept of a z-score, so there's not really a need to memorize or write down a new formula just for this. It's the same thing, just one we would then use for t-distributions and the other we would use for normal distributions. Now, there is an equivalent here also if you're using sampling distributions. So if you're using a sampling distribution for the mean, then you would take x minus x bar divided by s over the square root of your sample size. Exact same formula as what we did with normal distributions. Again, you're just using the standard error, which is going to be the standard deviation divided by the square root of the sample size you're using. But you have to calculate those sorts of things first. And then you plug into this formula because the TI doesn't provide any of those helpful included inputs for those things. Inverse t. Inverse t calculates a t-value or t-score, which has an area of whatever p your input is here to its left. That's really important because there is no option to change it to right-oriented area or center-oriented area with respect to the inverse t function. In fact, some of you with TI-83s, if it's old enough, you might not even have an inverse t function, in which case you'll probably want to use the stats calculator in place for that calculation because there's no other way you're going to come up with that value. But the TI, it's always left-oriented. And no matter how new your calculator is, it's always left-oriented. So it's just important to understand that difference. So all the little niceties that the TI provides for normal distributions, it leaves us in the dark when it comes to t-distributions. Unfortunately, that's the distribution that we're going to use the most going forward. So we have to understand all the little details of how to do this stuff ourselves instead of relying on the calculator doing all the convenient things for us. Now, for those using the online stats calculator, I'll explain in detail what you need to know as I get into examples later on. It's similar in operation to how you did normal distribution calculations, but I'll show you everything, when we do some examples. So one application that we're going to use t-distributions for will be the creation of confidence intervals when that population standard deviation is unknown. If a small sample is being used, there's one additional criteria. You see, the central limit theorem guarantees that your sampling distribution will form a normal distribution under two conditions. One, if your sample size is large, so if it's bigger than 30, you're guaranteed that the sampling distribution, I guess technically I should say a bell-shaped distribution. It's not necessarily a normal distribution, but it's bell-shaped. If you have a small sample, you need to know that the original population that you're pulling from is normal to begin with, or at least approximately normal in some way, so that the central limit theorem will guarantee that for the small sample, that sampling distribution will be bell-shaped as well. And so we can continue with the theory of small samples with that additional piece. We have to know the original population's approximately normal. If it is, then we're okay to use the t-distribution in order to convert our level of confidence into a critical value. And the way we do that is through a very similar formula for a critical value. You see the critical value formula here for t-distributions looks almost identical to what it was for normal distributions. It's just instead of using inverse t, we use inverse norm, and then you provide it the 1 minus c divided by 2, and remember that is the area in the lower tail of your distribution. So when you have a distribution of data and you're trying to center your level of confidence, whatever you choose that to be, you're trying to center that about the mean. In order to figure out these two values here, t sub c and positive t sub c on the right end, you take 1 minus your level of confidence, which gives you the amount of area in the tails of your distribution. And if you divide that by 2, then that will tell you in particular how much area is in the lower tail. So 1 minus c divided by 2. And that is the area to the left of this value right here, which is what inverse t can look up for us. But do keep in mind, we have to know the number of degrees of freedom, which you'll be told in the problem that you're using a sample size of 15 or 35 or whatever. You just need to know that the degrees of freedom is just one less than your sample size. But otherwise, we calculate that in the exact same way that we did for normal distributions. The next step in creating our confidence interval is to calculate the margin of error. And this is done with a formula that is really identical to the formula that we had with respect to normal distributions. On normal distributions, we used z sub c, the critical value that we got with respect to the normal distribution, times sigma over the square root of n. But if sigma is unknown, that population standard deviation, we're substituting s here and using the t-distribution value instead. But it's still essentially the same formula. And once we get that margin of error, the last thing that we need to do is create our confidence interval. And to do that, we just simply add and subtract the value of the margin of error to our point estimate. And our point estimate this time is still x bar. This is going to be the sample mean, and it makes up the center of our confidence interval. So your sample mean is one value, and your population mean could be somewhere else. I mean, it could be something else. But you're trying to estimate the value of this population mean with the value of x bar. But it's very unlikely that x bar actually equals mu. So you give some margin of error, which gives you two different points, an upper bound and a lower bound of an interval. So all these points in between are included on this interval. And then it's much more likely that the population value actually exists on that interval than it does just that one single point estimate. So we're doing the same thing. The only difference here is that we are using the t-distribution to come up with our critical value instead of the normal distribution. So let's take a look at some examples. Example 1. Construct a 90% confidence interval for the length of the poison dart frog if a sample of 25 poison dart frogs has a mean length of 32.2 millimeters with a standard deviation of 4.8 millimeters. You may assume the population is normally distributed. Okay, so just like we did with normal distributions, we have 3 steps here. Our first step is to figure out what our critical value is. Once we have that critical value, the next thing that we need to do is we need to get a margin of error. And then lastly, we then come up with the confidence interval. And the only one that really looks different at all is step 1, and that's just because we're using the t-distribution instead of the normal distribution. But let's go through all the details here and just kind of make sure everything is in place. All right, so first off, the thing we're being asked to do is to construct a confidence interval. And so it doesn't say for the mean, but later on in the problem, we have that the poison dart frogs have a mean length of 32.2 millimeters. We have a standard deviation, so we're going to construct this confidence interval for the mean. Okay, but the level of confidence that we're using is given to us then as 0.9. Now, what I'm going to do is I'm going to convert that to a critical value, t sub c, by using the absolute value inverse t, 1 minus 0.9 divided by 2, comma, the number of degrees of freedom. All right, so the sample size we're using. We have a sample of 25 poison dart frogs. So that means I have 24 degrees of freedom. It's always one less than the sample size, and that can be confusing as to when you're supposed to use 24 or 25. But in the calculation of your critical value, you're going to use the degrees of freedom. Now, to do this on the stats calculator, just like with normal distributions, under the distributions menu, you have normal distributions, and right below it, students t. And when you go into that function, it doesn't really look much different than the normal distribution calculator. You have an additional parameter here for degrees of freedom, and you can change that number of degrees of freedom, and I believe, yeah, it makes the curve look a little different depending on the number of degrees of freedom you're using. But ultimately, it works in the same way. You can provide x bar, the mean of your sample, your standard deviation of your sample if you like, or you can just use what's called a standard t-distribution and just leave that as 0 and 1 as well. But make sure the degrees of freedom are set properly. So I'm going to change that to 24 and use that. Now, the next thing is that you can calculate areas between two z-scores to the left or to the right, depending on what your situation is. So you have a bit more freedom here in the t-distribution calculator than the folks using the TI calculator. It's just designed a little bit more efficiently. The way that we came up with these critical values, however, we switched to the inverse mode. So remember, this is the CDF style calculations, and this is the inverse style calculations. Now, we want the area centered about the mean. So we want this area to be centered, and if you're in this between mode, it will do that, just like with normal distributions. So, in fact, you don't actually have to worry about this conversion here using the stats calculator. You didn't have to worry about it with normal distributions, and you don't have to worry about it with t-distributions either. Just change this over here to 0.9, your level of confidence, and then hit calculate or press enter, and it will come up with the two z-score values, or t-score I should say, that have 90% of the area between them for a standard t-distribution with 24 degrees of freedom. So 1.711 we'll say. And you just use the positive one. That's fine. All right, the margin of error. This isn't any different than what we did with the normal distribution. The formula is practically the same. It's that critical value that we just found times the standard deviation of the sample divided by the square root of the sample size. So in this particular case, it would be the 1.711 times the sample standard deviation, which was 4.8 millimeters, divided by the square root of the sample size, which is 25. So this is where it gets a bit confusing. You use degrees of freedom here, but this is, in fact, your sample size, n. So the formulas tell you what to put. You just have to read the formulas and listen to what they're saying. All right, so we need to make this calculation. So we'll go over here to the calc screen. So it is 1.711 times 4.8 divided by, and then that's the square root of 25. Okay. We get 1.64. I'm going to put a line between those, separate the calculations. Okay, that's our margin of error. And then lastly, we need to get our confidence interval, which just says to take your point estimate plus or minus that margin of error that we just came up with. So the point estimate here was the mean of the sample, so 32.2. And then we're going to add and subtract. I'm going to round this to 1 decimal just to match the accuracy of the original mean and standard deviation, but use the rounding that's kind of hinted in the problem. All right, so this would then be 32.2 minus 1.6. So I just need to calculate those things. All right, so 32.2 minus 1.6. So that's 30.6. And this is going to be in millimeters. Less than, and then this would be 33.8 millimeters. So to interpret this, we would say that we're 90% certain that the actual population mean value of the poison dart frog is somewhere between 30.6 millimeters and 33.8 millimeters. Now you see, that really wasn't much different than what we did with normal distributions. You're just using the t-distribution calculation to get that critical value, but otherwise everything's basically the same. Let's see the next example. A sample of 38 monarch butterflies finds that the mean time spent within a chrysalis is 12.3 days with a standard deviation of 4.2 days. Find the 95% confidence interval for the true population mean length of all time of the time that all monarch butterflies spend inside their chrysalis. Okay, so we're being asked to find a confidence interval, and in particular it's a confidence interval for the mean. Now we'll have to choose then if we're going to use a normal distribution or a t-distribution. So we look to the standard deviation. All right, so this standard deviation right here, this is, we have this sample of 38 monarch butterflies, and that sample finds the mean is 12.3 with a standard deviation of 4.2. So this is kind of telling us that of this sample of 38 butterflies, we have a sample mean of 12.3 days and a sample standard deviation of 4.2 days. So the population standard deviation is not known, so we're not going to use the normal distribution. We'll use the t-distribution as long as the central limit theorem thinks it's okay. And the central limit theorem will think it's okay if, 1, the sample size is bigger than 30, which it is. Whoops, didn't mean to zoom in there all that way. So that's greater than 30, so the central limit theorem's happy. The other case is that if it was smaller than 30, but the original population was at least somewhat bell-shaped, then that would be okay as well. But here we have a large sample, so we're fine. All right, so the first thing that we do is we take our level of confidence, which is 95% in this case, and we use the calculation to figure out what the critical value is. So we're using inverse t. All right, I'm going to come over here to the student's t-distribution calculator. Make sure you change the number of degrees of freedom. That's going to vary from one problem to the next. So the degrees of freedom in this case is 37. It's one less than the sample size. All right, now I'm in the calculate an x value. That's the inverse calculation. I'm centering the calculation about the mean. And then I want this value here to be 95%, so 0.95. So I want 95% of the data balanced about the mean. So that tells me my critical value here is 2.026. Okay, I usually take that to a few decimal places. The more you use, the more likely that you won't have any rounding error. And that's important, of course, with the homework. So just use as many as you're comfortable with. All right, we have a critical value. The next thing is to get the margin of error. The margin of error is just that critical value multiplied by the standard deviation divided by the square root of our sample size. So the square root of the sample size, in this case, is 38. All right, now when I calculate this using the stats calculator, I'll come up with the value of the margin of error. So let's go to the calc screen and start entering this calculation. So 2.026 times 4.2 divided by the square root of 38. Now, when I press enter, I get the value of that margin of error. So 1.38. And when I have that margin of error, all I need to do then to finish the problem off is to add and subtract it to the point estimate, which is 12.3. So to get my confidence interval here, I take the point estimate of 12.3 and I add and subtract to that. I'm going to round it to 1.4 just to match the accuracy. All right, but that's going to be, let's see, that would be 11, so 10.9 less than mu less than 13.7. So somewhere between 10.9 days and 13.7 days. We're 95% confident that the true population mean length is going to be somewhere between 10.9 and 13.7. That's how we interpret that value. Now, before I go on to the next example, there is one other thing I want to talk about here in terms of the use of a t-distribution versus a normal distribution. You see, the thing about the use of the t-distribution is because we're using the sample standard deviation instead of the population standard deviation. And the population standard deviation is an exact value. You know, it's the actual value of, you know, the standard deviation for your entire population, whatever it is. The sample standard deviation is just an estimate to that. And so it's not necessarily as accurate. So because of that, our confidence interval needs to get to be a little bit wider. And you may or may not be able to see that in all examples, just based off of what the sample size is and, you know, the numbers themselves. But let's try it here. Like, let's see what would happen if I were to do this with the normal distribution instead. So if I use the normal distribution and calculated the z-score that is balanced between the 95% balanced about the mean, that is. All right, so that z-score is 1.96, which is a little bit smaller than the 2.02. And if this multiplier becomes a little bit smaller, then a smaller number times this value, which would still be the same, would make this a little bit smaller. So it's going to make the margin of error smaller. And if the margin of error is smaller, then you have a smaller interval. If the margin of error is bigger, you get a wider interval. So if I took this value and changed it into 1.96 instead, well, there we go, I would get 1.335, which would be like 1.34, slightly less than this. So I would get a, you know, I have a slightly wider interval here because I am using the t-distribution instead of the normal distribution. And that's always going to be the case. Your t-distribution is always going to provide a slightly wider confidence interval than the population mean. Excuse me, than the normal distribution would. And it doesn't have to be by much. Like, this would round to slightly different values, but it's possible. Like if I was using a sample of 50 monarch butterflies, that these wouldn't even round any differently. But there is always going to be a slightly wider interval using the t-distribution. Just good things to kind of keep in mind conceptually here. Our last example here says that the femoral lengths of 5 known Tyrannosaurus rex skeletons in centimeters are given below. Assuming the data come from a population that is normally distributed, construct a 90% confidence interval for the mean femoral length of the Tyrannosaurus rex. Okay, so in order to do this, we generally have started off the problems knowing things like the number of items in the sample, the mean of the sample, the standard deviation of the sample, and then the level of confidence that we need to use. Well, we're being asked to construct a 90% confidence interval for the mean. Okay, so we know that. We have these 5 data items, so we know the sample size, but we don't know the mean and the standard deviation. So very often problems kind of start you off there, but they don't have to. Like, they can just give you a set of data, and then you should know that it's your job then, step 1, to figure out the mean and standard deviation, which we could do fairly easily using the stats calculator. We can just put our data into L1, so 126.5, 131.2, 127.8, and 128 and 78.8. Okay, once that data is in, we can calculate the mean and standard deviation. We just come over here, I'll clear this out, and I'll hit single var stats, and I'm doing this for the data contained in list 1. So when I press enter, it's going to come up with the mean and standard deviation for me. So the mean is 118.46, and the standard deviation, make sure you would use a sample standard deviation, because we don't know, well, it's probably pretty unlikely that this is the entire population of Tyrannosaurus rex that ever existed. It's a sample. All right, so 22.24. Okay, now that we have these values, we can start the problem off just like the others. So the first thing we need to do is come up with a critical value, and we would use the t-distribution if the conditions are met here. So first off, we certainly are not going to use a normal distribution because we have a small sample, so that's out the window. The original population, however, we're told we can expect it to be normally distributed. This is a population from nature, so that's probably going to be the case. And the t-distribution then can be used. So go over here to students t. We have 5 degrees of freedom. Oh, sorry, a sample size of 5, which means we have 4 degrees of freedom. All right, that updates. And then we are doing a 90% level of confidence. So we change this value to 0.9, press enter, and 2.132. That is our critical value. Okay, then we need to get our margin of error, which we take our critical value times the standard deviation, 2.4 there, divided by the square root of our sample size, which is 5. Okay, and go back to the calculator here, and on the calc screen, type this in to come up with our value here. So 2.132 times 22.24 divided by the square root of 5. So that is 21.2 centimeters. Okay, which is a pretty large margin of error here, but the thing is, I mean, we're talking about, animals that haven't existed for millions and millions of years, and we only have 5 of them anyway, so that's really not that bad, given how large these things were anyway. So now we can come up with our confidence interval. And based off of this confidence interval, which would be the point estimate plus or minus the margin of error that we just found. So our point estimate here is 118.46. Oops. And did I just round that to? Oh, it was 21.20. So, all right, so that's fine. Plus or minus 21.20. All right, but I would need to take 118.46 minus that. So 118.46 minus the 21.20, which is 97.26. Less than mu, less than, and then over on the other side, we just add those values together. And when we do that, we get 139.66. So we can say now that we're 90% certain that the actual population mean value of these femoral lengths is somewhere between 97 and 140 centimeters. All right, which is a pretty decent estimate, again, given how long ago these things lived. Now, there is one last thing I want to show you here. So for instance, when it comes to calculating confidence intervals, the TI provides some more convenience features, and those are available to you for confidence intervals for t-distributions as well. So if you go under the estimates menu, you have a z confidence interval of the mean, which is what we had used. In the last section, we used z confidence interval for proportions. Then you'll also find t confidence interval of the mean. So if you want to use this to check your work, that's great. But certainly make sure you do know the process for the tests. So like in example 2, we had a mean of 12.3 days, a standard deviation of 4.2 days, a sample size of 38, and a level of confidence of 95%. Now, what's really nice is with this, you're just giving the sample size, not the degrees of freedom, because the calculator knows to use the degrees of freedom when it needs to, and it's going to adjust and do that for you. So what we come up with then are just the endpoints of the interval, which hopefully match what we had here previously, and they do. So 10.9 and 13.7. So okay, and I also want to show you something nice about when you have data. This function also can take its input from data what happens is it switches off the boxes. You can't edit the mean, standard deviation, and sample size any longer, but you can edit what list is being used. And if you have your data already in L1, then you can just reference that data, press calculate, and what it will do is it will calculate the mean, standard deviation, and sample size for you. So those are presented down here. It will then come up with the critical value, which doesn't, oh, I didn't update the level of confidence here. That's better. and so it will come up with the mean, standard deviation, sample size for you, calculate the critical value based off of the given number of degrees of freedom, which would be 4 in this case, and then also provide to you the endpoints of the confidence interval, which does agree with what we had come up with here. So you can use that again for convenience and checking your final answer. Certainly, I think it's important when you're doing the homework to make sure you have the same decimal places, because depending on how many decimal places you round along the way, it can really have an effect on your final answer, and the homework's very picky about that sort of thing. So I would recommend, at least at the end of your calculation of these things, use that just to kind of double check everything, and then make sure any errors are just due to rounding, and then use that as your answer in the homework.